Well, welcome everybody to Question of the Week. This is the Facebook Live session in which I take on your science faith questions. Every Monday, 9:30 a.m. Pacific Standard Time, 12:30 in the afternoon for those of you on the East Coast. Today, I'm broadcasting at a special time and in a special location, Pine Mountain, Georgia, which is about an hour and a half south of Atlanta, Georgia. I'm on the Impact 360 Institute campus. I'm here doing a short course on science and faith for the gap year students that are part of the Impact 360 program. I'll talk a little bit more about what Impact 360 is and again what I'm doing here at the end of the broadcast. In the meantime, I will post in the edited broadcast description some information about Impact 360 for those of you who might be interested in what this program is about. It's a worldview training program that goes on for a year. It's a program in which the leaders of Impact 360 try to develop student leaders that will be the leaders in the church in the next generation. So it's an honor, it's a privilege for me to be here at Impact 360. This week's question comes from Billy Grimes, who wants to know about the second law of thermodynamics and how does it apply and impact the theory of evolution. And I'll take on Billy's question in just 1 minute. But before I do that, I want to remind you that if you're watching this live or even watching a recording of this broadcast, please go ahead and post in the comment section your location. Say hi, we'd like to hear from you. We want to know who's watching this program and where you're from. Also, if you just want to react to this broadcast, that's very much appreciated. So go ahead and use the like button. And then finally, if you are interested in offering your perspective, your comments on this week's topic, please go ahead and do so in the comment section. Even if you disagree with me, your perspective is definitely welcome. And I think you're going to find this week's broadcast a little bit controversial. At least for some of you, you might find it controversial. And so if you don't agree with me, that's wonderful. Go ahead, post those comments in the comment section. Okay, without any further ado, let's go ahead and get started here with Billy's question. Billy writes this question. Dr. Rana, Biologos says that evolution is not affected by the second law of thermodynamics. Is that true? This is a subject that comes up in my apologetic study group. Is this a valid argument against evolution or not? Could you be so kind to point me to some answers? Thank you very much. And what I will do is I will post the link in the updated description of the broadcast to the Biologos article that Billy Grimes is referring to. And Billy, like you, I hear this argument used all the time as a way to challenge or counter the theory of biological evolution. And I'm really glad that you asked about whether or not this is a valid argument and that you did a little bit of research before you actually encouraged other people to use this argument or that you use this argument yourself. So hats off to you for doing that. I personally think that this is not a good argument to use against the theory of evolution. Now, believe you me, I think there are some very powerful scientific evidences that we can point to that a creator must have played a role in bringing about the origin of life, that a creator must have played a role in the design and even the history of life. But I do not think that we should be using the second law of thermodynamics to make that argument. There are some very real scientific challenges to the theory of evolution, particularly when it comes to the origin of life and the design of biochemical systems. But again, the second law of thermodynamics is not a valid challenge to the theory of evolution. And what I'd like to do is explain why that is the case, and then how I see the second law of thermodynamics as somebody who is an ID proponent / creationist. So, okay, let's go ahead and unpack this whole argument. And before I do that, I want to make a point here, and this is a very important point to me anyway. is that when we are engaging people who are skeptics or who are seekers, and we're trying to build a scientific case for the Christian faith, we really have got to be careful that we're making strong, scientifically credible, scientifically valid arguments. We've got to do the best that we can towards that end. Because if we present a scientific challenge to evolution or a scientific argument for a creator's handiwork, and that argument lacks validity, what will happen is people that are in the know, people that know what's going on, are simply going to dismiss everything that you have to say if you make a faulty argument. They're just going to simply think that you don't know what you're talking about and dismiss everything you have to say. And so if you are making powerful, valid arguments, those are going to be lumped in with the bad arguments and are going to be discarded. So we want to do our homework. And again, my hat is off to Billy for doing his homework. So thank you, Billy, for setting an example for us. Now, why is it that I think this is not a valid argument? Well, we need to understand what the second law of thermodynamics is and what it isn't, okay? Now, many people have the impression that the second law of thermodynamics says that whenever a process or a transformation happens in the universe, things will go from order to disorder. That's not what the second law is actually saying. Now, that is part of one aspect of the second law of thermodynamics, but it's not what the second law of thermodynamics is about. The second law of thermodynamics has to do with what happens to the quality of the energy in the universe when a transformation or a process takes place. And the second law says that the quality of the energy goes from high quality that would be available to do work to low quality, where less energy is available in the universe to do work. And so energy always goes from high quality to low quality. And that's why heat flows from a hot object to a cold object. It's related to this idea of the quality of the energy in the universe and the capacity of that energy to carry out work. So things are never going to go from, heat is never going to go from a cold body to a hot body. The quality of energy is never going to become greater in the universe. Now, this is where Biologos is making a point when it comes to their article about the second law of thermodynamics and the theory of evolution. Because it is possible that in a local system that the energy quality can actually get higher. The energy quality can increase. Or that heat can flow from a cold body to a hot body in a local system within the universe. If that system is open and you can input energy and matter into the system, that you can violate the second law of thermodynamics, quote unquote, for a local system, because the overall effect on the universe is still that the entropy of the universe increases, that the energy quality of the universe decreases. The higher the energy quality, the lower the entropy. The lower the energy quality, the higher the entropy. So entropy always increases in the universe, but it can actually decrease in a local system. Now, where does this idea that when processes take place in the universe, things go from order to disorder, where does this idea come from? Well, it comes from statistical thermodynamics. This is the idea of applying statistical mechanics to individual molecules that are part of a system, and from the behavior of those molecules trying to develop thermodynamic expressions, thermodynamic quantities. And when you do that for entropy, the way in which the statistical thermodynamics works out is that you represent a system as all the possibilities for those molecular components, all the possible configurations for those molecular components. And it turns out that an ordered configuration is just one of a vast number of possible molecular configurations. So for a system that is closed, no matter can go in and out. That's adiabatic. No heat can go in and out. Systems will go from order to disorder because the molecules in the system are moving around, and they're going to very quickly go from that ordered state, which is one of a large possible number of states, to one of the other states, which is deemed as a disordered state. But again, if you have an open system, you can actually have, from a statistical thermodynamic standpoint, things going from disorder to order. That is possible because you're putting energy into the system, you're putting heat into the system, or sorry, not energy, but a matter into the system. And so that can essentially, in a local system, increase the order, decreasing the entropy, because the overall entropy and the overall quality of the energy in the universe is going to diminish. So again, biologos is correct by pointing out that in a closed adiabatic system, things will go from order to disorder, but that's a special type of thermodynamic system. If it's an open system, that law or that requirement does not apply. Now, something else that we have to keep in mind when it comes to applying thermodynamics to the theory of evolution. Thermodynamic quantities like internal energy, like enthalpy, like entropy, like the Helmholtz free energy or the Gibbs free energy, are state functions. That means that those qualities or those values, those quantities that we're using to describe a system only apply to the initial state of the system and the final state of the system. That's what is meant by that these are state functions. They're telling us nothing about the pathway to go from the initial state to the final state. That doesn't fall under the purview of thermodynamics. For a chemist, that would be under the umbrella of chemical kinetics. It's not a part of thermodynamics proper. And so, for example, when you're talking about whether or not something will happen, whether a process will happen spontaneously in nature, if a process is a process thermodynamically allowed, you're not really focusing on entropy, by the way. You're focusing on Gibbs free energy. Gibbs free energy is G, and that's equal to H, which is enthalpy, minus T, temperature, times S, which is entropy. That's how you assess the spontaneity of a process, is if the Gibbs free energy is negative, the process is thermodynamically allowed. It'll go from the initial state to the final state. If the Gibbs free energy is positive, the system will not undergo a transformation. It is not thermodynamically permissible. However, you can manipulate an open system by putting in heat, by putting in or by altering the temperature, by altering the volume of the system, by altering the matter, the concentration of materials, and you can drive something that is thermodynamically not allowed, that is, it has a positive delta G, to a system that has a negative delta G. Again, and so if you're applying this to the theory of evolution, you can't have a system locally decreasing in entropy. You can have a system going from disorder to order, and you can have something that under certain sets of conditions is non-spontaneous become spontaneous by, again, having energy and matter flow in and out of that system. And so again, because we're looking at localized systems, because again, in the overall context of the universe, the energy quality will decrease. And so there is a decrease in energy quality, an increase in entropy that is allowing that system to undergo a decrease in entropy and an increase in energy quality. Okay? And a beautiful example of the idea of a state function can be found by looking at some of the different states of carbon. Two of the most commonly recognized forms of carbon are diamond and graphite. Diamond is a higher energy state than graphite. Graphite is a lower energy state. So to transform carbon from a diamond form to a graphite form is a spontaneous process, thermodynamically speaking. It has a negative delta G. However, that process almost never will happen, or will happen on an extremely slow time scale, because the pathway to go from diamond to graphite is an arduous pathway. There's a very high energy of activation for that process. And so from a kinetic standpoint, it's not going to happen, even though it's thermodynamically allowed. So this is why it's very important that we pay attention to this concept of state functions. Now, something else to consider. As a biochemist, I don't see entropy as a disordering force, but as an organizing and an ordering force. Why? Because biochemicals are organic materials. And when you dissolve organic materials in water, they interact with the water, which is the solvent. They interact with the water molecules. Some organic materials are polar and they readily dissolve in water. And when they do, the water molecules that surround that polar material will actually be more disordered or be disordered. And because you're going from a solid material where you have a high degree of crystal organization to one where that material is dissolved in the water, that is basically increasing the entropy of the system, and that is a thermodynamically permissible process that has a negative delta G. However, if you have materials that are hydrophobic, that do not interact with water, they will not dissolve. Why? Because even though you're taking a solid material and you're dispersing it within the solvent, which is increasing the disorder of the system, the water molecules surrounding those hydrophobic materials actually become ice-like. They become ordered, and consequently the overall entropy of the system will actually decrease. The system will become more ordered because of the water solvent. This is called the hydrophobic effect. And because of the hydrophobic effect, the individual components that make up cell membranes, phospholipids and proteins, will spontaneously actually organize into a cell membrane bilayer structure. Protein chains will fold into complex higher order three-dimensional shapes that are more ordered than a disordered chain. The DNA double helix will form as a result of the hydrophobic effect. And in fact, cells will actually form, or at least in principle they could form, because of the hydrophobic effect, where you could actually argue, contrary to what we would think, that a cell is actually in a higher entropy state than the individual molecules that make up the cell because of the hydrophobic effect. And so for me as a biochemist, I see the second law as an ordering process, as an organizing force, not as a disordering force. And in fact, I actually see the second law of thermodynamics as part of the anthropic principle, as part of the design in the universe that makes life possible. Because not only does the second law allow metabolism to happen because of the directional flow of energy from high quality to low quality, but it also allows for structures that we need for life to form. So I see the second law as a powerful piece of evidence for God's role in the origin and the history of life and the design of life, but because it's an ordering force and has the just right properties that make life possible. Now, another thing that we have to consider too is something related to non-equilibrium thermodynamics. Most of the equations that you see in physics books and in physical chemistry books are equilibrium thermodynamics expressions. These are expressions developed mathematically when you take a system at equilibrium and you very slightly perturb it, and then you look at what happens to that system and you develop mathematical equations to then describe what's going on there. And those, again, equations are helpful under equilibrium or near equilibrium conditions. But if you move away from equilibrium conditions to what are called non-equilibrium conditions, very different sets of mathematics have to be developed. In fact, Ilya Prigogine, the French physicist, won the Nobel Prize for his pioneering work in non-equilibrium thermodynamics. And many people argue that the origin of life process is happening under non-equilibrium conditions. And one of the things that happens when you develop mathematical expressions for non-equilibrium thermodynamics is that matter spontaneously organizes into what are called dissipative structures. But that ordering of those dissipative structures is actually allowing for the entropy content of the universe to increase. It's counterintuitive, but it falls out of the mathematics, and there's been experimental demonstration that these dissipative structures actually do form. And so over the course of the last year or so, this scientist from Harvard University, Jeremy England, has received quite a bit of attention because he claims to have solved the origin of life problem. What he's doing is he's picking up after Ilya Prigogine, following in his footsteps and applying these non-equilibrium thermodynamic expressions to the origin of life question, and arguing that there's nothing in thermodynamics that prohibits the origin of life from taking place if we think about it under conditions of non-equilibrium thermodynamics. So now, the point here is that if you're going to critique evolution, you're going to critique the origin of life, thermodynamics is not the arena to critique it in. Now, how would we then critique the origin of life? How would we critique evolution? By focusing on the mechanism that needs to transpire to move the system from one state, one thermodynamic state to another. So you could argue, let's say, with respect to the origin of life, that maybe the cell is actually in a higher entropy state than the individual molecules that make up the cell. Counterintuitive because the cell displays so much order and organization, but we would make that argument again because of the hydrophobic effect. However, the pathway to go from organizing those individual molecular components into a cell involves so many steps, and the reasonableness of each of those steps is highly questionable. And so from a mechanistic standpoint, you could argue that even though the origin of life is thermodynamically permissible, mechanistically it's not ever going to happen because the pathway is too arduous and too unlikely for it to transpire, particularly given the conditions of the early Earth. It would be analogous to looking at the transformation of a diamond into graphite. Thermodynamically permissible, but the energy of activation is so high that that process never happens. And you could argue along those lines for why the origin of life, for example, though thermodynamically permissible, would never transpire because of kinetic considerations, because of the pathway required for that transformation to take place. So anyway, great question, Billy. I hope that this helps clear things up a little bit for you and for other people. And again, it's very important that we really understand what's going on before we start making arguments. And there are things relating to the second law of thermodynamics that, in my experience, are really very poorly understood by many people. And, you know, I've had the benefit of basically having some very good physical chemistry courses as an undergraduate and as a graduate student where some of these ideas were fleshed out. But working in membrane biophysics and biochemistry, this idea of the hydrophobic effect and the fact that cell membrane formation is entropically driven, is an entropy-driven process, is inherent in that particular area of biochemistry. And I've had a lot of exposure to bioenergetics, and where, again, there are ideas that are in the popular vernacular about the second law that are just simply not valid. And again, you've got to do your homework before you start making arguments against the theory of evolution. That's kind of the key point here today. And please don't use the second law to argue against the theory of evolution. It's just not a valid argument. Okay, now let me go ahead and just take one quick second to remind you that if you want to ask a question for next week's question of the week, go ahead and post that question in the comments section of this Facebook Live broadcast. Also, you can post the question on my Facebook page, or you can send me a private message, and I'll consider the questions that come in this week. Also, I'm keeping track of questions from previous weeks, and I'm trying to identify those questions that I think are intriguing, that are provocative, but also are going to be of widespread interest to people that are concerned about the relationship between science and the Christian faith. A couple of other things real quickly. Again, I'm here in Pine Mountain, Georgia on the Impact 360 campus. This is a wonderful program that I've just been recently exposed to in the last few years. It is called a gap year program. The idea is that Christian students, as they graduate from high school, before they go to college, will take a year off from their studies and immerse themselves in worldview training that helps them to fully understand the Christian worldview, how to defend and articulate the Christian worldview in a university environment. It also is a program where there's leadership development that takes place, where there's spiritual development that takes place. It's a wonderful program that really equips the next generation of leaders in the church and gives students a vision for how they can not only be successful in a college environment, but how they can actually provide a very powerful witness for the Christian faith because of their excellence in critical thinking and their excellence in scholarship. And it's also a wonderful privilege to have Reasons to Believe partner with Impact 360, not only through my involvement as teaching the Science Faith course, at least the last year and this year for Impact 360, but also we are partnering with Impact 360 for our program called The Lab. This is a 3-day unique mentoring program that we provide for Christian students who are in high school and college who are looking to pursue careers in science, technology, engineering, and medicine. And this year, in early June, I think it's June 8th through the 10th, we're going to be holding a lab here on the Impact 360 campus. And so if you're interested in learning more about that, I will also post a link to the lab for this upcoming June in the description for this broadcast. So anyway, I'm going to go ahead and sign off here. And I just want to let you know that, again, I really appreciate your interest in my ministry, in the work of Reasons to Believe. I also want to express my gratitude for your prayers and your support for our work. And so, again, much appreciated. If you've got any feedback for how this broadcast could be improved, I would love to hear it. And I'm just going to leave you with this final thought, that the more that we know about science, the more that we have reasons to believe. God bless you. I'll see you next week.